Electrochemistry, Part 5, Electrolysis and Faraday's Law. For this video, we will be performing calculations of the amount of charge flow based on the changes in the amounts of reactants and products in an electrochemical cell. Essentially, we'll be doing some electrochemical stoichiometry. Recall that an electrolytic cell is the process of using electricity to drive an otherwise non-spontaneous chemical change. This is used to force an unfavorable reaction for many useful applications, including refining ores, electroplating, production of hydrogen and oxygen gas from the electrolysis of water, and also the production of chlorine and sodium hydroxide from the electrolysis of salt. We can do calculations regarding electrolysis by using Faraday's law, which is really just based off the definition of current. Electric current is how quickly charge is flowing. The symbol I represents current in the equation I equals lowercase q over lowercase t. Q is the charge in coulombs, and t is the time in seconds. The SI unit for current is amperes, or more simply amps, and is equal to a coulomb per second. For our purposes, it will be probably better to see the capital A for amps and think of it as coulombs per second instead. Because we're going to be using it as a dimensional analysis conversion factor between charge in coulombs and time in seconds. Based on Faraday's law, we can use some stoichiometry calculations for redox reactions to determine things like how many electrons are being transferred, the mass of materials deposited or removed from an electrode during a reaction, the amount of current itself, the total time elapsed during electrolysis, and even the charge of an unknown ionic species. Let's take a look at a couple of examples. Do you have your dimensional analysis skills all warmed up? Here's a sample problem where we need to figure out the mass of copper that will deposit on the cathode in an electrolytic cell after 30 minutes of 10 amps based on this half reaction that's given. To do this, we'll simply convert the time to seconds so that we can use the current of 10 amps, that is 10 coulombs per second, to convert seconds into coulombs. Then we can use Faraday's constant to get coulombs into moles of electrons, so that we can use the half reaction's coefficients to convert moles of electrons into moles of copper. Then our old pal molar mass is going to take us home, converting the moles of copper into grams of copper. We see that after 30 minutes of 10 amps, we'll have almost got 6 grams of new copper on our electrode. Now let's go the other direction. If we want to get 10.5 grams of silver metal from an electrolytic reduction of silver ion at 5 amps, how long do we need to run the cell? Pause the video and use some dimensional analysis to figure this one out. Did you get 31.3 minutes? I did. Here's how. Using the molar mass of silver, I converted grams into moles. Using the coefficients from the half reaction, I converted moles of silver into moles of electrons. Using Faraday's constant, I converted moles of electrons into coulombs of charge. And using the current of 5 amps, that is 5 coulombs per second, or in this case 1 second per 5 coulombs, I converted coulombs into time. Then I converted to minutes, because that's just how I roll. I hope this video has been helpful for getting you to apply Faraday's law to an electrolytic redox reaction. If not, let me know. Thanks for watching.